How to find the bounds of a triple integral. When a triple integral is applied to a function, it gives us a hypervolume. This hypervolume comes from the space that is bounded by a given three-dimensional region and the surface of the function. If, however, we apply a triple integral to a function that is always equal to 1, then it simply gives us the volume of that three-dimensional region. In either case, you want to recognize that the bounds of the triple integral are describing some three-dimensional space. This means if we can fully describe the surfaces that make up that region, then we can quickly and easily build the bounds for our triple integral. To do this, we can use the method of collapsing. In this method, we choose a variable or direction to walk through the region. We then describe the surfaces that we must enter and exit as we move through it. These surfaces are described by functions, and they become the bounds of our integral. Specifically, these bounds will be on the integral associated with our direction of movement. Finally, the region collapses onto the remaining axes so that we can repeat the process for the remaining variables. Let's see how this works when our region is being described using rectangular coordinates. Here we have a region that is being bounded by three surfaces. The top is being described by the plane z equals y plus 1. The bottom is the parabolic cylinder z equals x squared plus 1. And the side is the plane y equals 1. We can begin by choosing to move through this region in the z direction. As you can see, we'll have to enter in the bottom of the parabolic cylinder, and we'll have to exit out the plane. So the bottom bound will be x squared plus 1, and the top bound will be y plus 1. Now let's collapse our region onto the remaining variables of x and y. Now our region is much simpler since it only has two dimensions. Like before, we want to choose a direction to move through this region so we can build our next set of bounds. Let's choose the y direction. In this direction, we would enter along the bottom surface given by the parabola y equals x squared, and we would exit out the line y equals 1. So the bottom bound is x squared and the top bound is 1. Now let's collapse in the y direction, leaving us with just a thin region on the x-axis. Since there is only one variable left, we can now only move in the x direction. Now we'll be entering at the point x equals negative 1 and exiting at the point x equals 1. This gives us our final bounds. It's important to note that the order in which we choose our variables does not matter as long as our function is continuous inside the region. To see this, let's reset our region and come up with some brand new bounds. We'll begin by moving through the region in the y direction. This will force us to enter the slanted plane of z equals y plus 1 and exit out the plane y equals 1. These, of course, will become our bottom and top bounds. Since we are moving in the y direction, we must describe both of these surfaces in terms of y. So the bottom bound will be z minus 1 and the top bound will be 1. We can now collapse our region on the remaining variables of x and z. Let's now move through the collapsed region in the x direction. As you can see, we'll enter the left of a parabola and exit the right of a parabola. This parabola is given by the equation z equals x squared plus 1. This may seem like a problem, but remember, we're moving in the x direction, so we want to describe these surfaces in terms of x. Subtracting 1 from both sides and taking the square root, we see that we get two surfaces from our one equation. X equals negative the square root of z minus 1, and x equals the square root of z minus 1. These will become the bottom and top bounds of our integral. We now collapse in the x direction. This leaves us with a thin line segment along the z-axis. As we move through this region, again in the z direction, we would enter at z equals 1 and exit at z equals 2. These are the remaining bounds of our triple integral. Keep in mind that even if the order of our variables does not matter, we should still pick the order with care so that our bounds are nice and simple. This is especially true if we need to evaluate this integral once the bounds are set.